Hi, and welcome to Smart Edition's Anatomy and Physiology session on the lymphatic system. My name is Galen. I'm a registered nurse, and I'll be presenting the information to you today. Let's talk about the lymphatic system. This is a really interesting system in the body. So what is it? It consists of a network of vessels, organs, and tissues that are distributed throughout the body. Its major functions are pretty diverse. They include things like protecting the body from invaders and harmful cells, so it's part of the immune system, also maintaining a healthy fluid balance, and then helping with the absorption of some fats. So you can see that those kind of cover a wide variety of different functions. And here is an illustration of how the lymphatic system is indeed distributed throughout the body. It's very similar to our circulatory system. You can see the vessels in green that almost look like our veins in our arteries, but are different, as we'll see. So the lymphatic system includes the following structures: the spleen, the tonsils, the adenoids, the appendix, the thymus gland, and the lymph nodes. And as you can see, comparing that list to our illustration, this is not an exhaustive list of structures found within this system. They're just the ones that we're going to highlight today. So the largest of the lymphatic organs is the spleen. It's located above your stomach and underneath your left rib cage. It's this red structure highlighted here. The spleen has a wide variety of functions. It helps fight certain types of bacteria. In addition, it acts as a filter and it takes old, abnormal, or non-functioning blood cells out of circulation. It also helps store blood. So you can see just a sampling of the spleen's many important roles in our bodies. The tonsils, the adenoids, and the appendix are really interesting organs. For a long time, the medical community and scientists thought that they were vestigial. That's a word that means that they had lost their useful functions over time and were just kind of sitting in the body, serving no useful purpose in our modern day and age. However, after years of study, scientists have now discovered and now believe that each of these are actually parts of the immune system. They have immune functions. So the tonsils, if you open your mouth and stick out your tongue and say ah, you can see them hanging down the back of your throat. So they're located at the back of the throat, and the tonsils, along with the adenoids, which are located behind your nasal passage, form part of the first line of defense against germs that enter through your mouth and your nose. So in the food that we eat, in the fluids that we drink, also in the air that we breathe. So they kind of help filter out those germs, the tonsils and the adenoids, which are not pictured in our illustration. The appendix is part of the digestive system. So it potentially supports the immunity of this system, the GI system. Scientists believe that it might serve as a reservoir for good gut bacteria, so bacteria that actually helps support the regular functioning, the healthy functioning of our digestive systems. So for example, if you have, say, an illness that causes diarrhea and everything kind of gets flushed out of your GI system, then the bacteria that found like a safe harbor in that appendix, once your body has healed from that GI disease, will be able to come out and repopulate the gut and get back to a normal functioning, help it get back to normal functioning more quickly. So you can see how each of these organs actually do indeed have helpful immune functions, but it took us a long time to be able to recognize that, and there is still a lot about each of these that we don't know, so they're still under study. Now, scientists also believe that all three of these organs are potentially most active during childhood, especially early childhood, which makes sense because in early childhood, our immune systems are very much still developing. After early childhood, they think that maybe other parts of the immune system take over the majority of immune functions. Another important part of the lymphatic system is the thymus gland. This is a gland that is located directly above the heart. It's a little bit difficult to see on this illustration, so I'm going to put my mouse over it right here. It's this peach-colored gland located here in front of the heart. The thymus gland secretes hormones that stimulate the maturation of killer T cells. And if you're thinking, I don't know what those are, don't worry. We're going to cover those a little bit later on in the presentation. The thymus gland is interesting because it's only active from birth through puberty. After puberty, it decreases in both size and functionality. Lymph vessels, if we go back to our previous illustration, are those things that I said look like blood vessels but are green, are responsible for transporting lymph. This is the name for the fluid of the lymphatic system, along with white blood cells. So these vessels carry lymph only in one direction. They collect it from the tissues of the body and they return it to the subclavian veins where it re-enters circulation. And you can see those, if we go back to our previous slide, you can see the subclavian veins illustrated here as well. So those are actually blood vessels, but they are part of the lymphatic system in the sense that lymph is returned to them to re-enter circulation. As you can see in this illustration, the lymphatic vessels contain one-way valves which help keep lymph moving in the right direction. And interestingly enough, the movement of surrounding arteries and muscles near the lymph vessels helps maintain this forward flow of lymph as well. In addition, we have lymph nodes. These are connected to the lymph vessels and they serve as filtering stations. They filter through lymph and remove and destroy harmful pathogens, foreign toxins, and broken or abnormal cells. So anything that's potentially harmful or damaging to the body, they'll help filter through and remove and destroy. All right, so let's ask some practice questions to help us kind of solidify this information that we've just covered. Which of the following organs was never considered vestigial? Was it A, the adenoids? Was it B, the appendix? Was it C, the spleen? Or was it D, the tonsils? And the correct answer here is option C. The spleen was never considered vestigial. So remember, that is a term that means that organs have lost their useful functions over time and they're kind of just sitting in the body. They once had a purpose, but in our modern day age, they no longer serve a purpose. And scientists once believed that the adenoids, the appendix, and the tonsils were vestigial organs, although nowadays we understand that they actually do play a role in the immune system. The spleen, however, was never considered a vestigial organ. Its important functions have long been recognized, and so that is our correct answer, option C. Before we move on to the rest of the content, I want to remind you that you don't have to stress when preparing for your TEAS exam. Our TEAS online course eliminates the guesswork of what to study. Our practice tests are realistic, our videos are detailed and easy to follow, we offer a mobile app, and more for one low price. Check out our online course at www.smarteditionacademy.com. Now let's jump back into the A and P review. Which gland is only active from birth through puberty? Is it A, the adenoids? Is it B, the appendix? Is it C, the thymus, or is it D, the tonsils? And the correct answer is option C, the thymus gland. So remember that this gland secretes hormones that stimulate the maturation of killer T cells, and it's only active from birth through puberty, as we've noted. Why is this the case? Well, around the time of puberty, the body has all the T cells that it will need for life. So after this point, the thymus gland decreases in both size and functionality because essentially its job is complete. It's done its work. It's supplied the body with the necessary T cells that it will need for the rest of life, and it is no longer required. Its services are no longer required. You can think of it that way. Now remember that we said that scientists believe that the adenoids, the appendix, and the tonsils might also, similar to the thymus, be most active in childhood, especially early childhood, after which other parts of the immune system kind of take over the major role of defending the body. However, these don't have the puberty cutoff that the thymus gland has, that distinct puberty cutoff. And so the thymus gland is indeed our correct answer here. The other options are incorrect. All right, so now that we've kind of introduced some of the key parts of the lymphatic system, let's dive in a little more in depth into the actual immune response. So remember that helping fight foreign invaders, helping protect the body against potentially harmful substances is one of the key roles of the lymphatic system. And that's kind of the role that we're going to be focusing on throughout the rest of this presentation. So as soon as a pathogen, which is another word for a foreign invader, enters the body, the immune system kicks into gear and begins to fight it. It's important to note that the body has multiple types of immune cells, but for the purpose of our presentation, we are going to focus on 4 of those. These include 2 types of lymphocytes, B cells and T cells, of which we'll focus on 2 subtypes, as well as macrophages. So what do each of these cells do? Well, helper T cells activate both killer T cells, we've seen that term before a little bit earlier on in the presentation, and B cells. They also produce defensive proteins. Killer T cells attack and kill cells of the body that have been infected by pathogens. Killer T cells have receptors that can recognize tiny bits of the pathogen's proteins. So when they encounter an infected cell that has these proteins on it, killer T cells are able to release enzymes into that infected cell that encourage the infected cell to destroy itself. This process is known as apoptosis. B cells label invaders for later destruction by macrophages. B cells have receptor proteins called antibodies on their surface. Each antibody is unique and protects against a specific antigen. Antigens are unique identifier proteins found on pathogens. They basically let the body know that this is something that is potentially harmful and an immune response needs to be mounted against it. B cells can release copies of their antibodies either directly into the bloodstream, where they'll float around until they come in contact with a pathogen, at which point they'll attach themselves to it, tagging that pathogen for later destruction. Or B cells can actually put antibodies directly onto pathogens themselves. So if they themselves come into contact with a pathogen, they can tag that pathogen with an antibody themselves. Macrophages consume pathogens and infected cells in a process known as phagocytosis. Macrophages also play a role in initiating basically an alarm signal that activates the helper T cells. So you can see how none of these 4 types of white blood cells work in isolation. Instead, they all exchange information, they correlate their activities, and they work together as an integrated system to defend the body against harmful substances and foreign invaders. So, a couple practice questions here. Which of the following is the correct series of the lymphatic system's defense mechanisms? Is it A, B cell and killer T cell, then macrophage, then helper T cell? Is it B, helper T cell, killer T cell, B cell, macrophage? Is it C, macrophage, helper T cell, B cell, then killer T cell? Or is it D, macrophage, helper T cell, B cell, and killer T cell? And the correct answer is option D. So remember that macrophages, in addition to consuming pathogens and infected cells through phagocytosis, also play a role in kind of sounding the alarm and activating helper T cells. Helper T cells in turn then activate both the killer T cells and the B cells, and they also secrete defensive proteins. As we've noted, killer T cells attack and kill infected body cells, while B cells tag pathogens for later destruction by the macrophages. So again, you can see how all four of these cells work together to mount a coordinated defense. Options A, B, and C contain the right elements of the lymphatic system's defense mechanism. However, they are in the wrong order. So we can eliminate all three of those as incorrect options, and we're left with option D, which is our right answer. How do the killer T cells recognize infected cells? A, the B cells flag the infected cells with amino acids. B, tiny bits of the virus's RNA are left around the cell. C, macrophages show up to help consume the infected cell. Or D, the T cells have receptors that recognize the proteins the virus left on the surface of the cell. And option D is our correct answer. So remember that killer T cells do indeed have receptors that are able to recognize tiny bits of the pathogen's proteins. So when they encounter a cell that has been infected by a pathogen and still has those residual little bits of proteins, then they release enzymes into that infected cell that encourage it to destroy itself. This is a process known as apoptosis. So right away we can eliminate option B because it's not tiny bits of the virus's RNA that the killer T cells are able to recognize, it's proteins, as we have seen. So B is incorrect. A is also incorrect because, as we've seen just a few slides ago, the B cells don't flag infected cells, rather they are flagging invaders, they're flagging pathogens, and they're not flagging them with amino acids, instead they're flagging them with antibodies. So A is incorrect as well as B. C is actually true. Macrophages do show up to help consume the infected cell. However, this is something that maybe happens after the killer T cells have already recognized them and encouraged them to destroy themselves. It is not a precursor to killer T cells being able to recognize infected cells. So while this is true, it's not necessary for the recognition of infected cells by killer T cells. We can eliminate that as an incorrect answer option as well. So C, B, and A are all incorrect, and we're left with D, which is our correct answer. The B cells label invaders for later destruction by blank. Is it A, antibodies? Is it B, macrophages? Is it C, proteins? Or is it D, T cells? And the correct answer here is option B. So in a way, you can think of macrophages as part of the cleanup crew in the immune response. So they're responsible for consuming both invading pathogens and infected cells through a process known as phagocytosis. Phagocytosis describes the destruction of a cell by engulfing it and breaking it down. So this is how the macrophages destroy both invading pathogens and infected cells. So B cells label invaders by using antibodies, which, as we've noted, are proteins. So A and C are not what destroy the invaders, but instead what the B cells use to label them. So we can eliminate those as incorrect. And then the T cells, remember there are two types. Helper T cells get activated by macrophages and in turn activate both killer T cells and B cells, while killer T cells destroy infected cells. So T cells are not responsible for destroying invaders. That role falls to macrophages. So B is our correct answer here. When a B cell encounters a foreign microbe with a surface protein that matches the shape of its antibodies, it attaches an antibody to the microbe. How does this help destroy the pathogen? A, the antibody invades it. B, the antibody consumes it. C, the antibody marks it for destruction. Or D, the antibody blocks the function of the microbe. So the correct answer is option C. Out of all these answer options, as we'll see momentarily, this is the one that most correctly identifies the function of antibodies in this context. But let's go into that in a little more depth. So when a B cell receptor connects to its specific antigen, so remember that each antibody, each receptor is specific to one particular type of antigen, a helper T cell releases chemicals that tell that B cell to divide many times. So the result is an army of B cells that all have a perfectly shaped B cell receptor to connect to the invading pathogen, which makes sense because the goal is the eradication of that pathogen from the body. And the more B cells we have that correct antibody, the more efficient the body will be at eradicating that pathogen. So remember, antibodies are proteins that are produced in response to and counteract specific antigens. Antigens, again, are foreign substances found on pathogens that induce an immune response. So attaching an antibody to an invading microbe labels it for destruction by macrophages, which destroy it through consumption. So B does not correctly describe the function of antibodies, it describes the function of these macrophages. So B is incorrect. A is also incorrect because this process of invading more correctly corresponds to the function of killer T cells, right? Which inject an infected cell with enzymes that encourage that infected cell to destroy itself. So A does not describe the function of antibodies either. A and B then are incorrect. And then D is incorrect as well. Antibodies do not block the functions of the microbe. Instead, they kind of act as a tag labeling that microbe for destruction, as we've seen. So A, B, and D are incorrect, and C is our correct answer. Why is a B cell that is stimulated by an encounter with a microbe to divide repeatedly and form a large population of identical B cells a positive addition to the body's defense strategy? A, the B cells engulf all the microbes. B, the B cells outnumber the microbes. C, the B cells produce large numbers of antibodies. Or D, the microbes retreat and are excreted from the body. And the correct answer here is option C. We want the B cells to produce large numbers of antibodies because, as we've noted before, antibodies are those blood proteins that are produced in response to and counteract specific antigens. B cells can either release antibodies directly into the bloodstream where they'll attach to any pathogen that they encounter, or they can attach them directly to pathogens themselves. And this labeling of these foreign invaders allows them to be identified more quickly and thus eliminated as a threat more quickly and more efficiently. So the more antibodies we have, the faster all of the foreign invaders will be located, labeled, and then subsequently destroyed. So option A, as we've noted, does not describe the function of B cells. Instead, that process of engulfing sounds more like phagocytosis, which is a role of the macrophages. So A is incorrect. We can eliminate that as an incorrect answer. And it may be true that once we have this large army of B cells, that they outnumber the microbes, but that's not really the point. The point is that we want to be able to find all of the microbes as quickly as possible and tag them for destruction so that the body can get rid of the threat as quickly as possible. So B is incorrect. It's not our best answer for this particular question. What about answer option D? Well, instead of the microbes retreating and being excreted from the body, I would say that what we want is more better described by total elimination of the microbes. than retreating and being excreted from the body. So we're going for eradication. We're going for total destruction. We're not going for just merely a retreat. So D is not a good answer either, and we're left with C, which is our correct answer here. Okay, so we've talked about some key parts of the lymphatic system. We've talked about the immune response. Let's now talk about some different types of immunity. And as you can see from this flow chart, immunity can be divided into multiple types or categories. So the first subdivision here is innate versus adaptive immunity. So innate immunity describes that with which we are born. We possess it all our lives. So it includes things like physical and chemical barriers within our bodies. So think things like mucous membranes. That mucus helps trap harmful substances and foreign invaders. Think also things like the hairs that are found in our noses that help trap and sweep out foreign invaders. Those are part of innate immunity. We possess them throughout our lifetimes. They don't need to develop. We are born with them. In contrast, adaptive immunity is that which is acquired over our lifetimes. So we don't stop with innate immunity. This is like the starting point. You can think of it as that. And then adaptive immunity builds off of that. That might be a helpful way to think about it. So as you can see, adaptive immunity is also subdivided into different categories. So we have natural and we have artificial, and each of those are divided into both passive and active. So what do all those terms mean? So natural adaptive immunity is that which is gained through processes that virtually every human experiences in the course of their lifetime. And that'll become clear as we discuss the specific examples of passive and active. So hold that in your mind for a second, and let's talk about artificial immunity before diving into that. So artificial, I keep saying immunity. Artificial immunity is not that which would occur normally over the course of a person's life. Instead, it has to be administered through some sort of artificial means. And again, that'll be clear as we dive into this next subdivision of immunity. So what do passive and active mean? Well, active means that the body is actually going through the work itself of mounting an immune response. So your own immune system is responsible for protection against that pathogen, that foreign invader. This results in long-term immunity because part of the immune response is the development of memory cells, which allow the body to remember fighting against a particular pathogen and allow it to defend more effectively against that pathogen should it be encountered again later on in life. So that's active immunity. Your body is actually doing the work itself of defending itself. Whereas passive immunity is given to you. It is gained another way. So this type of immunity, passive, is short-term because your body is not actually going through the work of producing antibodies against whatever pathogen it's being defended against. They are not continually replenished. Those memory cells that I mentioned in active immunity are not formed. And so this type of passive immunity will dissipate over time. So let's look at specific examples. As you can see, both natural and artificial can be divided into natural passive, natural active, and then artificial passive, artificial active. So what's an example of natural passive immunity? Well, a great example of this is babies receiving immunities from breast milk. So the process of breastfeeding is normal, right? Something that many babies will experience in their lifetimes. And so in that sense, it's natural, but it's passive in that the baby's body is not producing these immunities. It's receiving them from its mother. In contrast, natural active is developed, for example, when we get an infection, when we become sick by a pathogen, and our bodies work to produce antibodies to combat that particular illness. So as you can see, the body is doing the work, so memory cells will be made against this pathogen. What about artificial passive? So this is also temporary immunity. A good example of this is the administration of immunoglobulins. So in this sense, the immunity is immediately available. However, as we mentioned before, because the body is not actually doing the work itself of developing immunity, eventually that immunity is going to dissipate because no memory cells have been made. So this will require continued doses to maintain immunity. And in contrast, artificial active, a great example of which is immunization with vaccinations, stimulates the immune response in a person's body to produce antibodies against whichever pathogen you're being vaccinated against. And so this, similar to actually going through an infection or an illness, results in the creation of memory cells and long-term immunity against that pathogen. So let's talk a little bit more about that, vaccination. So in vaccination, typically, either a dead or disabled pathogen or a harmless microbe that has had the proteins, the antigens, of that pathogen attached to it gets introduced into the body. As I mentioned a couple seconds ago, this triggers a lymphatic system response similar to what we would experience if we were actually infected with that pathogen and we're experiencing some kind of illness as a result. But the beauty of vaccinations is that it does not produce an actual infection. So the vaccinated person's body produces memory cells directed against that particular pathogen, which then remain in their bloodstream and result in long-term immunity, but without having to go through the process of getting ill and dealing with that actual infection. Vaccinations have really dramatically reduced the incidence of many serious bacterial and viral diseases, some examples of which include polio, tetanus, and diphtheria. One particularly poignant example is an intensive vaccination program that took place in the 1970s and led to the virtual elimination of smallpox, which historically has wreaked havoc on humans. So vaccinations have offered us as a society a lot of protection and have led to the virtual eradication of some diseases that, like I said, historically have really negatively impacted us and caused a lot of disease, death, and disability. All right, so let's ask some practice questions about the various types of immunity that we have covered. When a child breastfeeds, that child is exposed to all the germs on the mother. As a result, what type of immunity is the child acquiring? Is this A, artificial active? Is this B, artificial passive? Is this C, natural active? Or is this D, natural passive? And the correct answer here is option D. This is a perfect example of natural passive immunity. Breastfeeding is a natural process. The child is obtaining immunity to various pathogens without actually getting sick. And so that means that this is a passive process. So again, just a perfect example of this type of immunity. In contrast, natural active immunity would mean that the child was actually getting sick and their immune systems were going through the process of developing an immune response against that particular pathogen that caused that sickness themselves, rather than just passively receiving them from the mother. So C is incorrect. An example of an artificial passive type of immunity would be the administration of immunoglobulins, as we've discussed, which results in an immediate immunity, but also a temporary immunity. And then artificial active, the best example that we have of that is vaccination, as we've discussed at length. So A, B, and C are better described with different examples. The one that makes the most sense for this particular example is option D, so that's our correct answer. Which type of immunity does the MMR vaccine provide? Is that A, artificial active? Is it B, artificial passive? Is it C, natural active? Or is it D, natural passive? And as we've discussed, vaccinations confer A, artificial active immunity, because they are artificial. Something is being given to a person as opposed to them actually going through the typical experience that pathogen would produce should they encounter it like just through the course of their normal lives. But it's also active. It's producing an actual immune response within that person, just without them becoming ill. And this results in long-term immunity because memory cells are made since the body is actually doing the work of mounting a defense against that pathogen. So B, C, and D are provided via other means, as we've already discussed. They're not good examples of what type of immunity a vaccination would provide, so we can eliminate those as incorrect answers, and we'll stick with A, which is our right answer here. Why is a vaccinated person said to be immunized against a particular disease? A, the number of helper T cells has increased. B, the number of macrophages has increased. C, antibodies used to fight that disease have been produced. Or D, histamines used to fight that disease have been produced. And the correct answer here is option C. So antibodies is that key term. So remember, these are proteins produced in response to and counteracting specific antigens found on foreign invaders. Again, those antigens label for the body the fact that this is indeed something foreign, potentially harmful, and in need of mounting an immune response against. So once these antibodies have been produced against that particular pathogen or foreign invader, the person's body will make and retain memory cells that are directed against that pathogen. So if that person is infected by that pathogen again, the body will be able to more quickly and effectively respond to eradicate the infection, either before symptoms are even produced or in a way that greatly lessens the impact of that infection. So it could be much less severe than it would be if the person had not been vaccinated. And again, the key term here is antibodies. It's not helper T cells, it's not macrophages. Those play a role in the immune response, but not in remembering the pathogen. So A and B are incorrect. And then D is also incorrect. We'll discuss histamines a little bit later in the presentation in the next section, but they are part of the inflammatory response. They're not part of being immunized, as we'll see. So C is our best answer here. Now, sometimes people complain that they've become sick because of a vaccination, but why is this impossible? A, the pathogen is dead. B, the pathogen was originally harmless. C, the pathogen is only viable for a short time. Or D, the pathogen has been disabled by sterilization. The best answer here is option A. So remember that typically vaccinations contain pathogens that are either dead, that have been disabled, or they've removed the antigens from that pathogen and attached them to a harmless microbe. So it's impossible for vaccinations to cause illness because it's either been dead, it's been disabled, or it's just its antigens attached to a microbe that does not cause illness. Now, vaccinations do produce an immune response, and this can sometimes lead to symptoms like a fever. In this case, what people would identify as sickness actually means that the vaccine is working well. It's doing its job. It's producing an immune response which will result in long-term immunity. So that is what is more likely causing the symptoms that this person is experiencing than the vaccination itself actually causing a sickness. B cannot be true because we don't vaccinate against pathogens that are harmless. Like, we only vaccinate against pathogens that have the potential to cause a great deal of harm to us. So B doesn't make sense as an answer, and we can eliminate that as incorrect. C might be true, that the pathogen is only viable for a short time. However, that's not the point. The point is that the pathogens in vaccinations have been killed or disabled or have had their antigens removed and attached to a harmless microbe, which is what is actually getting injected into a person's body. So C is not a good answer either. And then D is not a good answer because pathogens, there are many different ways by which pathogens are disabled. Sterilization is just one of them. So this is not a good answer because it's a little bit too narrow. So D, C, and B, we can eliminate them all as incorrect. And the best answer, as I've said, is option A. So that's the one that we're going to go with. Okay, so in the rest of our time here, we're going to talk about some different diseases and disorders of the lymphatic system. And the first category that we're going to discuss is autoimmune diseases. So we've talked about how both killer T cells and B cells are able to distinguish the body's own cells from foreign cells. And this ability is crucial, one, for the fight against pathogens, being able to correctly identify foreign invaders, but two, to the health of the body itself. In autoimmune diseases, this ability to correctly distinguish between our own healthy cells and foreign cells breaks down, and the result is that the body actually attacks its own healthy, normal cells. There are many different types of autoimmune diseases, but the following chart gives some examples of maybe some of the most well-known or common ones, or at least the ones that you need to know for your upcoming nursing entrance exams. So the first is systemic lupus erythematosus, and that's a really long name. It's kind of hard to say. This is more commonly known as lupus. Lupus affects many areas throughout the body, or it can. Some common ones are connective tissue, joints, and the kidneys. It has a lot of symptoms, but some include facial skin rash, painful joints, fever, fatigue, kidney problems, and weight loss. Type 1 diabetes affects the insulin-producing cells in the pancreas. Some symptoms of this autoimmune condition include excessive urine production, blurred vision, weight loss, fatigue, and irritability. Graves' disease is an autoimmune condition that affects the thyroid. Symptoms include weakness, irritability, heat intolerance, increased sweating, weight loss, and insomnia. And then finally, rheumatoid arthritis is an autoimmune condition that affects the joints. A common symptom of this condition is crippling inflammation of those affected joints. So you can see something that I want to point out before we move on is that many of these conditions have overlapping symptoms. For example, weight loss is one that you see on multiple of these, as well as irritability. And there are other symptoms that overlap as well. This is not an exhaustive list. And this can make it difficult to pinpoint exactly which autoimmune condition is affecting an individual. And that can be further complicated by the fact that sometimes individuals have multiple autoimmune conditions going on at the same time. So this is pretty complex, or at least it can be. So another thing that can affect the lymphatic system is just the normal process of aging. As we age, our bodies produce fewer B and T cells, and as a result, our ability to defend ourselves against viruses and bacteria decreases. This is why the elderly are more susceptible to disease, particularly severe particularly severe infection, because their bodies are just less efficient at defending themselves. Allergies represent another disorder of the lymphatic system. In this case, the body's immune system is actually working too well. So it's attacking itself or responding to substances that would typically be harmless. So antigens, we've discussed those, are found not only on pathogens, but also on many different types of substances, including harmless substances. When you have an allergy, the body detects these antigens and it feels like they present a threat, even though in most people they typically wouldn't. So think things like foods, think things like dust, for example. Most people will not, their bodies will just recognize these as, oh, it's harmless. But in people with allergies against those particular things, the body encounters the antigens and it mounts an immune response against it. So hay fever is a common example. So mast cells are cells that are attached to white blood cells. They line the entrances to the body. When they encounter matching antigens, as is illustrated here, they initiate an inflammatory response, which includes the release of substances called histamines. We mentioned those a little bit earlier on in the presentation. So among other things, histamines cause capillaries to swell, mucous membrane production to increase, and these can lead to symptoms that we would associate with an inflammatory or allergic response. And then the final disease of the lymphatic system that we're going to discuss is HIV or AIDS. HIV stands for human immunodeficiency virus. AIDS stands for acquired immunodeficiency syndrome. So this virus is the result of a mutation that occurred in a virus that originally was affecting chimpanzees. So it mutated and allowed it to jump over into humans. This virus results in the collapse of the lymphatic system, as you can see here, because it targets and destroys both macrophages and helper T cells. It also uses macrophages as a reservoir, which means a population, tissue, etc., that is chronically infected with the causative agent of a disease, in this case HIV, and thus can act as a source of further infection. So HIV kind of sets up camp in these macrophages, uses them to hide out from the immune system in a person's body, and kind of uses them as a base to continue attacking the body and proliferating. Because there's no cure for AIDS, prevention is key. HIV, AIDS can only survive in blood and body fluids because that's one of the places that we find macrophages. And as we said, it uses these macrophages as reservoirs. The primary means of transmission then is through sexual intercourse. In other words, a way that a method that allows for the exchange of body fluids, that allows their insertion from the infected person into another person. HIV cannot be transmitted through the air, on toilet seats, or by any other medium where a macrophage cannot survive. In other words, those that don't involve the exchange of blood or body fluids. So it can't be transmitted through shaking hands, sharing food, or drinking from a water fountain because macrophages can't be transmitted through casual contact. Okay, we'll end our discussion today with a series of practice questions. Why is it crucial for killer T cells and B cells to distinguish cells of a person's own body from foreign cells? A, they can divide and conquer. B, they develop more antibodies. C, they will only attack cancer cells. Or D, they will not attack the body's cells. And the correct answer here is option D. It's crucial for killer T cells and B cells to be able to correctly identify foreign cells, not only so that they can effectively eliminate threats, but also so that they don't attack the body's own cells. When the immune system mistakenly attacks healthy, normal cells in the body, this can result in an autoimmune disease. And as we've noted, there are many different types of autoimmune diseases, and they often present with similar symptoms, which can make it hard to pinpoint which particular condition a person has. But a classic sign that's present across most autoimmune diseases is the presence of inflammation. In other words, redness, heat, pain, and swelling. And that makes sense when we think about the immune response. C is not a good answer because we don't want these cells to only attack cancer cells. We want them to attack all legitimate threats to the body, which includes more than just cancer. So we can eliminate that as incorrect. And then both A and B are more descriptive of the normal functioning of the immune system. We want our cells to work together efficiently and produce the appropriate amount of antibodies. But what we're specifically being asked about in this question is why it's important for them to be able to distinguish cells correctly. And the best answer for that, as we've seen, is option D. So we can eliminate C, B, and A. Option D is our correct answer. Rheumatoid arthritis, attacks on membranes around the joints are an example of A immunity, B pathogen, C allergic response, or D autoimmune disease. And as we've seen earlier in the presentation, rheumatoid arthritis is an example of an autoimmune disease. So when the immune system mistakenly attacks healthy normal cells like the membranes around the joints, in this particular example, this is known as an autoimmune disease. Rheumatoid arthritis, or RA, is often found in many joints at once, but most commonly affects the hands, the wrists, and the knees. It causes the linings of affected joints to become inflamed, which ultimately results in damage to that joint tissue and symptoms such as chronic pain, lack of balance, and deformity in those affected joints. RA can also affect the lungs, the heart, and the eyes. So pretty devastating disease here. What about our other terms? Immunity describes the process of being protected from a pathogen, as we've seen earlier when we were talking about different types of immunity. A pathogen is a foreign entity that invades the body and causes harm or illness, infection. There are 5 different kinds, kind of broad categories of pathogens. These include viruses, bacteria, fungi, protozoa, and worms. And then C, an allergic response, we've described that as like a hypersensitivity of the immune system. It's working too well to the point where it's responding with an immune response to substances that should not typically induce an immune response, like food, for example, or things that we would encounter in our environment. So C, B, and A are describing different scenarios, different processes than what we're being asked about in our practice question. D is our correct answer here. Which autoimmune disease exhibits the following symptoms: facial and skin rash, painful joints, fever, fatigue, kidney problems, and weight loss? Is it A, type 1 diabetes? Is it B, Graves' disease? Is it C, rheumatoid arthritis? Or is it D, systemic lupus erythematosus? And answer option D is our correct answer. So lupus, for short, is a chronic autoimmune disease that can cause inflammation in any part of the body, as we've already stated. But most commonly, it affects the skin, the joints, and internal organs like the kidneys, heart, and brain. There is no single defining symptom of lupus. It can affect each person differently. Common symptoms include, but are not limited to, those discussed here: painful and swollen joints, as well as muscle pain, fever, a red rash, which we've noted is often on the face and is typically called the butterfly rash, chest pain with deep breathing, hair loss, sun sensitivity, mouth ulcers, fatigue, and swollen glands. So the symptoms are very individualistic because they depend on where in that particular person the lupus is causing inflammation. There's no cure for lupus, but lifestyle changes and medication can help manage it. So we've already talked about rheumatoid arthritis, and though it has some overlapping symptoms with lupus, like the inflammation and the painful joints, this particular cluster of symptoms does not describe rheumatoid arthritis, so we can eliminate that as an incorrect answer. And then what about A and B? Well, type 1 diabetes, we said that's an autoimmune condition that affects the insulin-producing cells in the pancreas. So though similar to rheumatoid arthritis, some of the symptoms overlap with lupus. This particular cluster of symptoms does not best describe type 1 diabetes. And the same is true for Graves' disease. This is an autoimmune condition affecting the thyroid. And this particular cluster of symptoms does not most describe Graves' disease either. So A, B, and C we can eliminate. Option D is our best answer for this cluster of symptoms. Now, which of the following diseases exhibit symptoms such as weakness, irritability, heat intolerance, increased sweating, weight loss, and insomnia? Is it A, type 1 diabetes? Is it B, Graves' disease? Is it C, rheumatoid arthritis? Or is it D, systemic lupus erythematosus? And this particular cluster of symptoms best describes option B, Graves' disease. So as we've stated, Graves' disease is an autoimmune disorder that results in hyperthyroidism. It causes your immune system to attack the thyroid and results in the production of more thyroid hormone than your body needs. So common symptoms do include what we have listed here. Since the thyroid controls how your body uses energy, Graves' disease affects nearly every part of the body, and if left untreated, it can lead to serious complications and issues with the heart, the bones, the muscles, the eyes, the skin, the menstrual cycle, and fertility. So pretty serious condition, like many of the other autoimmune conditions, pretty devastating and debilitating. We've already discussed A, C, and D, and though, again, it's important to note that many of the symptoms of these other conditions might overlap with those that we see in Graves' disease, this particular cluster of symptoms best describes Graves' disease, and so that's our correct answer. We can eliminate the other ones based on what we've already seen regarding them. Now, what type of cells release histamines? Is it A, B cells? Is it B, mast cells? Is it C, helper T cells? Or is it D, macrophages? And the correct answer here is option B, mast cells. Remember that these are attached to white blood cells. They line the entrances to our bodies. When they encounter antigens that match their receptors, they initiate an inflammatory response. And part of that inflammatory response is the release of histamines. And among other things, histamines cause capillaries to swell and also increase mucous membrane production. So this is our best answer. We've talked at length about B cells, helper T cells, and macrophages. They all play different roles in the immune response, whereas mast cells are more particularly associated with the inflammatory response. So we can eliminate A, C, and D, and B is our best and correct answer here. Now, why is AIDS a devastating disease? A, it targets red blood cells. B, it targets respiratory lining cells. C, it targets many different types of cells. Or D, it targets the cells in the lymphatic system that target pathogens. D is our correct answer. A, B, and C don't correctly describe the targets of AIDS. So specifically, AIDS destroys macrophages and helper T cells. And if you'll recall from earlier in our presentation, both of these play a crucial role in the body's immune response. Without them, the body's ability to fight pathogens is extremely impaired. And as we've seen in the names of HIV, human immunodeficiency virus, as well as AIDS, acquired immunodeficiency syndrome, they both contain that word immunodeficiency. And so their names imply a failure of the immune system to adequately protect the body due to the absence or insufficiency of some vital process or substance. In this case, these two types of immune cells. So that is why AIDS is so devastating. So D is our correct answer here. Why is it impossible to transmit HIV through casual contact? A, the antibodies cannot exist in the air. B, the antibodies consume the macrophages. C, proteins signal T cells to consume the macrophages. Or D, the macrophages cannot exist outside human body fluids. And option D is our correct answer here. Remember that the HIV uses macrophages as reservoirs. And since macrophages can't exist outside human body fluids, HIV can't survive outside human body fluids either. So it can't be transmitted through casual contact. There has to be that exchange of body fluids. We can eliminate options A, B, and C because they are incorrectly describing various components of the immune system. For example, HIV doesn't have antibodies, instead it has antigens. Antibodies are the proteins that respond to specific antigens, such as those found on HIV. And the other two examples are incorrectly describing different immune system components as well. So A, B, and C are incorrect. As I've noted, the correct answer is option D. Why is sexual intercourse the most common method of spreading HIV? A, because T cells are located in semen and vaginal secretions. B, because B cells are located in semen and vaginal secretions. C, because proteins are located in semen and vaginal secretions. Or D, because macrophages are located in semen and vaginal secretions. And again, option D is our correct answer here. HIV uses macrophages as reservoirs. It does not use T cells, B cells, or proteins. So we can eliminate A, B, and C as incorrect because that is our key word here that shows us that this is indeed our correct answer. And as we've noted in the previous practice question, since macrophages are found in the blood and body fluids, for example, semen and vaginal secretions, HIV can be transmitted via routes that involve the exchange of these substances, most commonly sexual intercourse. There's the exchange of these secretions. So D is our best answer here. Which of the following can transmit HIV? A, air, B, toilet seats, C, water fountains, or D, infected intravenous syringes. And the correct answer here, similar to the previous two practice questions, is option D. Because as we've noted, the macrophages, which HIV uses as reservoirs, are found in blood and body fluids. So HIV can be transmitted via any route that involves the exchange of these fluids or the putting of infected fluids into another person's body. If you're using an intravenous syringe, it's likely that there's residual blood from the infected person, for example, on that syringe or in that syringe, and so there's the potential for you to inject some of that blood into your own system, potentially leading to the transmission of HIV. So D is the correct answer. A, B, and C don't involve that exchange of body fluids, the putting of an infected fluid into your own body, and so they are not routes by which HIV can be transmitted. So they are incorrect. Thank you for sticking with me. Thank you for your patience with me today. Really quickly, if there is anything in the presentation that you feel like you need to review more in depth, please refer to the Smart Edition website. You'll find lots of content there that corresponds to the content and the order of the presentation that we've gone through today, and that will give you additional information for reviewing some of these things more in depth. There's also a practice test on the website, as there are with the other systems, and video explanations of the correct and incorrect answers. So take advantage of those resources, particularly if you feel like you need a bit more review on this system. And again, thank you for joining me today. I hope that you found this helpful, and I will see you next time. Have a great rest of your day.